And welcome to what will be the last of our films for Unit 38, and in this film, unlike the others, we aren't actually going to be making anything or using any physical components. This film centres on drawing things and simulating them, and the package we're going to be using for this is Circuit Maker. Circuit Maker is based on Spice, and if you were working in a research lab, you'd probably use something like MATLAB, possibly Eagle or AutoCAD, but in an academic situation, you'd be using a Spice-based simulator because usually they're freeware or very low-cost license. And they work perfectly well. They'll do anything you want to, within reason. So with that said, let's get on and see our first simulation and see what we can do. On to the first of our simulations then. What we're using is Circuit Maker. It's the student version, which is exactly the same as the professional version, except that you can only have 50 components on the workspace at any one time, and some of the more advanced features, such as PCB routing, are disabled. What we see in front of us is a big blank white screen, and that's because we haven't told it we want to make a new file yet. So what we do is, if I angle the camera here, we go to File, which, like any Windows program, is in the top left hand corner just here, and we say New. Now we're given a lot of options. We're given New, Open, Reopen, Import, Export and Exit. New is what we want to do, and up comes a workspace, and we'll make it a little bit bigger so that it covers the whole of the screen. There we are. So what we want to do here is we want to make a rectifier that turns AC into DC. We want to make it in the simulator and test it in the simulator. So the first thing we're going to need is we're going to need something to rectify with, and what we're going to use is a full bridge rectifier. Now, up in the toolbar here, up in the menu bar here, let me just turn the camera a little bit. Up in the menu bar here, there's one for devices, and if we click on it, what we can do is we can browse or we can search. I'm going to hit the browse button to start with, and that brings up a dialog box. And let's zoom in on that dialog box and see what we've got. Zoom in a little bit more so we can see it. There we are. And on the left here we have the major device class, which is a list of all sorts. And if I pick one at random, we've got connectors, another one we've got digital, and that gives me instruments and power, and then digital basics, which gives me the flip-flops, gates and whatnot. And going down we have fusers and modulators and all sorts of things. Silicon control rectifiers, timers, all sorts. Now the problem with doing it like that is I don't actually know where in this vast array the rectifier we want is actually kept. So there's a button here that says search. And so if we hit the search button, now what I can do is I can type in the word bridge and click this button here which says find, and it will give me a list of everything with the word bridge in it, and they should all be bridge rectifiers, and they are. So what I'm going to do is I'm going to select one, and I'm going to select an 18 dB2, which is 200 volts, 1.8 amps, and that should do nicely for this game. And if I hit the button here that says place, what it'll do is it'll let me place the bridge rectifier in the workspace. Now if I want to see it, what I need to do is I need to go back to the toolbar, and there's a button here with a magnifying glass on it, and if I click that and then I click on here, it will enlarge whatever I'm working on, and if I go too large I can press the shift button on the keyboard and click again and make it smaller. Now, there is another button here, and it's one with a little arrow on it, and that's my pointer button. And to manipulate anything, I need to be selecting the pointer button. So there it is, it's selected, and what I'm going to do is I'm going to select the text of the bridge rectifier, and I'm going to move it over here, because if I leave it where it is, it will be in the way of the work I want to do next. Now, it might not be terribly apparent here, but there's a little ghost there, and it's where the text, this text here, used to be. And if that happens, what you can do is you can go to the menu strip at the top, and you can click on View here. And when that happens, you get options here, and right at the bottom there's Refresh Screen. Click on that, and it clears away all the artifacts. So what we're going to do, back to Devices, up here, and we're going to go back to Search, because the next thing I want is an AC supply. And the AC supply is going to be provided by a signal generator. And again, I don't know where it is, so I'm going to find it. And there it is. So place, and in it goes. I'm going to zoom in on that a little bit before I do anything else, because at the moment it's putting out a sine wave. You can tell it's putting out a sine wave because that's a picture on the generator itself. And the amplitudes of the sine wave are -1 and +1 volts, and they are the maximum amplitudes, not the RMS. Now what I'll need to do is I'll need to select that thing. So back to my select button, and I turn it red by clicking on it, and then I right click to bring up this drop down menu. And I've got a lot of options in here. I can rotate it, I can mirror it, and there's edit signal generator, edit device data, edit pin data, device display data, and I can move it, delete it, duplicate it. But what I actually want to do is I want to edit the signal generator, which you can see just here. So clicking on that will bring up this dialog box. Let's zoom in on that. Now interestingly, I can change the waveform if I want. So I can have sine wave, pulse, an AM signal, an FM signal, an exponential, and piecewise. And piecewise is an irregular sawtooth wave. If I change it to pulse, now what I can do is I can set the initial amplitude, the pulse amplitude, period, and all the stuff to do with the wave. And as you can see, the picture on the front has changed, and so have the minimum and maximum amplitudes and the frequency. Well, I don't really want that. I want an AC sine wave, so we're going to do it again, and here we go. Edit signal generator, and instead of the pulse, we're going to go back to the sine wave. Now, at the top we'll see DC offset, and DC offset means that we can set the AC wave to not quite go back to 0, and I don't want to do that. I want that as it is, so I'm going to leave that there. However, what I do want is I want the peak amplitude to be 20 volts, and I want the frequency to be 50 Hertz. The start delay and the damping factor don't matter here. What they do is, obviously what the start delay does is it delays the time. The damping factor stops instabilities in the wave, but there shouldn't be any anyway at this, so off we go. OK. There we go, it's changed again, and the values are minus 20 and plus 20 volts, and it changes at 50 Hertz. Now, what we've got here is an AC supply, and normally that would be coming out of something like a transformer, possibly a switch mode supply, whatever it is, but we need to rectify that AC supply and we need to turn it into a DC supply, which is the job of this thing. So we'll zoom out so that we can see the toolbar, and on the toolbar there is a button just here, and it looks like a little plus sign, but what it actually is wires. So if I click that, what it will allow me to do now is to wire my two components here together. Like that. And zooming in a little, if we have a bridge rectifier and simulator, the AC supply always goes in the top and bottom, and the two sides here are for the DC supply. It'll be DC positive, that'll be DC negative. Right. So what we need to do now is we need to put in a load. And what I'm going to do is I'm going to put in a resistive load, and I'm going to simulate it by the simple expedient of putting a resistor in there. And I don't need to search for a resistor because I know exactly where they're kept here. There's a category called General, and it has all of the most frequently used things in there. So we've got bipolar junction transistors, capacitors, diodes, inductors, instruments, resistors and sources. So we want a resistor, and we can have the American standard or we can have the European standard, and we are European, so let's put the European standard in. Now I will need to rotate that a little bit, so what I do is I click the select tool, I highlight the resistor, and I right click and I select rotate 90 degrees, and there it goes. Again, click the wiring tool, and that allows me to wire up the components. So then, we could be ready to simulate. But before we do that, what we can do is we can look at a very important button. I'm going to tilt the camera so that we can see the toolbar, and zoom in so that we can see the button I'm going to talk about. And the button I'm going to talk about is this one here. Now if I zoom in a little bit more, you might be able to see that currently it's got a picture of a bipolar junction transistor in, an NPN one. And what that means is that the simulation it's going to do is an analog simulation. If I click that button, it will turn into an AND gate, and what that means is the simulation it's going to do is digital. Now all these buttons are these simulations, and this particular one here, where the man walking up steps, is the step simulation. You'll not use that very often. And this particular one here with the man running is the simulation running. So let's come out again and back to our circuit such as it is. Before we start simulating an analog simulation, there's one more thing we need to put in, otherwise it won't work. So we're going back to devices, and we're going to browse, and we're going to sources, and we're going to put a ground in, because for an analog simulation in this package, as in most SPICE packages, you will need to put in the pull down node, which is the ground source. And if I click it there, underneath that resistor, what should happen is it should attach itself nicely to the wire, and there we are. Well, we're ready to begin a simulation, so let's do it. We'll click on the little running man, Ah, ha, ha. Selected items in this circuit may not be simulated in the selected simulation mode. Continue simulation, no. And the reason for that is because I have left it in digital simulation and it's an analog simulation. So, I'll click on the simulation button to turn it back to analog and click run again. And there we are. And now one of the unfortunate things about this package is that it does tend to default in where it puts things. And so, I'm going to zoom out a little bit. And this bit here is my oscilloscope. Now I like my oscilloscope to be on the right hand side and my circuit to be on the left. So what I need to do is I just need to manipulate things about so that we can see things. There we go. And I like my oscilloscope to be pretty big. And my DC average multimeter to be under the oscilloscope. If I do that, I can move my circuit a bit bigger. And now, if I click in the view on menu bar, it gives me an option to fit circuit to window. You can also do that by pressing the key F4. So let's do it. And there we are. The circuit is now in the window and it's nice and big and we can see it, and we can also see the oscilloscope. So then, with my simulation running, I'm going to switch the oscilloscope on. And what I'm going to do first of all is I'm going to put the probe here and see what we've got. Now let's just zoom in on the oscilloscope here. A few important points. So, along the x-axis we've got the time, and at the y-axis we have the voltage, and as you can see it's going from 0 to 20 volts and dropping down again in a half cycle. So rise, fall, clip, rise, fall, clip. The clip is there because it's not measuring the other half of the cycle. Let's zoom out again and put the oscilloscope probe here so that we are measuring the other half of the cycle. And there you are. As you see, the crest and the clip have changed places. Swap them round again. There we are. Now, the job of the bridge rectifier is to take the two halves of the cycle and put them all the same way, so there'll be no negative. And if I put the probe of the oscilloscope here, what I should be seeing is crest, 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 and no clips. Well, let's see if that happens. And there we are, that's good. We know that the AC is doing what it should, and we know that the rectifier is doing what it should, and we see that the undulating waveform is going from 0 volts to about 20 volts. We're losing a tiny little bit through there, and back down to 0 volts again, but all in the same way. Now in electronics, that's really not a clean power supply. There are things we can drive with that. It's not too bad for things like lighting, but for sophisticated electronic devices, what we really want is something where the line is a bit more flat. So instead of seeing that undulating waveform, what we want to see is something that's more along the lines of a flat line, rather like this, which is the 0 volts. Now we'll never get it as perfect as that, but there are things that we can do to get it very near. So let's stop the run and we'll go back to devices And this time what we're looking for is a polar capacitor. And again, that's in general, and it's here in the capacitor section. So click on that, and there we are, a polar capacitor. Now, in this package we don't have the option of a European symbol for the polar capacitor, we only have the American one, so we're stuck with that, but never mind, we'll place it in. And I might have to do a little bit of rotating, so highlight it and right click, and rotate 90 degrees, highlight, right click, rotate 90 degrees, right click, rotate 90 degrees, there we are, and get rid of that down to there so that it's not covering anything up and it doesn't look too scruffy, and of course refresh the screen to get rid of the artifacts. Again, click the wiring button and wire the capacitor in parallel to the load. Now again, this is highlighted, so I'll click the select button, and if I right click on it now, I can edit the device data. What I can do here is I can change the value of the capacitor. I can also change the designation, but I don't really want to. By default, the package is giving me a 1 microfarad capacitor, and I could change that if I want to, but I'm not going to at the moment. What I'm going to do is I'm going to leave it as 1 microfarad, and we're going to see what happens on the oscilloscope. So, let's click the run button and put the oscilloscope here. Well, it doesn't look as though there's much difference, but what you'll see is that the minimum value of wave is coming down, and it's never quite reaching 0 anymore. And that's what the capacitor is doing. The capacitor is charging and discharging at a certain rate so that it'll never actually reach 0 anymore. What we'll do is we'll increase the value of the capacitor. So instead of 1 microfarad, we'll have 10 microfarads and see what happens. Well, that's had a big difference. As you can see, what we've got here is the capacitor charges up, and it discharges and charges and discharges, and it's never actually getting lower than, what, 10 volts? Well, that's fairly encouraging, so let's alter the value of the capacitor again to 100 microfarads and see what happens. And you can see that it's gone much more smoothly now. So let's just zoom in on the oscilloscope so we can see what we've got here. Well, this is a sawtooth waveform, and it's what we call in electronics a ripple. And that's quite a small ripple, just a couple of volts. But we can make it even smaller. And what we want is to get it so that you can barely detect the sawteeth in the waveform. So what we're going to do is we're going to stop the run, and we're going to change the value of the capacitor yet again, and we'll make it 1000 microfarads. Well, if we look at the oscilloscope now, we can see that the line has flattened out tremendously. And the ripple is much, much, much less than a volt. And that's probably good enough for most things. What we could do, if we wanted to, is yet again increase the value of the capacitor. 1000 microfarads, we'd probably put 2 capacitors in parallel, but just to simulate it, we'll call this a 2000 microfarad capacitor and see what happens next. and now there's barely anything there. It's a lovely smooth waveform. It's almost like true DC. We've looked at the waveforms, but another thing we can do is we can look at the output voltages. And what we really need to do is we need to get the output voltage as close to the input voltage as we possibly can. So let's go back to the circuit. And we'll look at putting a multimeter across the load, and we'll change the capacitor just as we've done before. This time we'll ignore what the waveforms look like and we'll see what the output voltages are. So we go back to devices and browse, and what we're going to do is we're going to pick instruments, and in instruments we will find a multimeter. Now then, as we place the multimeter we get some choices about what we want it to do. And to be a true multimeter, of course, it has to measure resistance, voltage and current. And we want it to measure the voltage. Now we've got a form of DC voltage here. What we want to do is we want to measure the DC average, not the DC. If we measure the DC, it probably won't show us a reading. So we measure DC average. We go OK. So let's wire the multimeter in. Like that. And we'll come out a bit so we can see the value of our capacitor, and we're back to 10 microfarads. Well, let's start the simulation running. Right, we've got 14.47 volts there. Let's increase the value of the capacitor to 100 microfarads. Now we've got 17.52 volts, and as you can see the waveform is much less ripply. And let's increase to 1000 microfarads. Oops. 17.92, looks as though that's as much as we're getting. We could increase it to 2000 microfarads and see what we get. No, we've actually dropped it a little bit there. So it looks as though about 18 volts is the maximum we're going to get, and that's due to what we're losing through the rectifier here. Still, it's a good exercise, this one, and basically what we've done is we've proved that we can turn AC into DC, or at least a form of DC, measure it, and look at the cleanliness or otherwise of the waveforms that come out. And we can do that for any form of analogue circuit really, so it doesn't matter what it is. As long as there is an analogue voltage running through there, we can measure it on the oscilloscope, and we can measure it with a multimeter, and we have all sorts of tools available to us in the simulation package to do that. Digital is a slightly different kettle of fish, and we'll be looking at that next. Well, in this section of the film then we're going to be looking at digital, and specifically we're going to be looking at how to use gates and how to simulate gates. And what we're going to do is we're going to open a new file, and we're going to put a couple of gates in just to get us started. So if I go to Devices and Browse, and in the Major Device class I want to be looking at Digital Basics. And if I look at digital basics across in the minor device class, I've got gates, and then I've got all the devices, 2 in AND, 2 in OR, and so on and so forth. I'm going to put a 2 in AND in there. There it is. And I'm going to put a 2 in OR as well. There it is. Well, let's zoom in a little bit. There we are. You can see what we've got. One way we can actually check what's happening with digital is that we can put in a thing called a logic display, and I'm going to do that now. So if I look in digital animated and I look in displays and logic display, there's one, and I'm going to put it on the output queue. There we are. Duplicate that, and there we are. And we also need to provide some sort of pulse at the inputs. And the way we can do that in a digital simulation is to go to digital on the major device class, power on the minor device class, and choose a thing called a logic switch. And if we put the logic switch there, and then what I'm going to do is I'm going to hide all the device data. Oops, not like that, I'm going to hide all the device data. And there's a bit here that you can't quite see, so I'll zoom out, called device display data. If I click on that, it'll let me hide all the data. And in that way, I don't get it scruffed up by text all over the place that I don't really need. So, we duplicate that, duplicate, stick it in there. If I now choose these two together, I can duplicate from the edit menu and I can put them in to the next one, and that just saves me a bit of time in drawing. So what I'm going to do now is I'm going to start the simulation and we're going to see how the logic display works. Except we're not, because I've forgotten to put it as a digital simulation. There we are. So this is an AND, and as we know, the truth table for an AND states that it will only give a high output when both inputs are high. So let's set both inputs high, and there's the logic display high. And this is an OR, and when either input is high, the output will be high too. And there we are. And that's one way that we can check and see what our logic is doing in the simulator. There are other ways, and we're going to look at those shortly. Now, for this circuit, I'm thinking of doing something like this. What this is an 8-input OR, and it's designed for an alarm system. On the right here we can see the analog part of our alarm system, and that's just basically a sounder. So we can ignore that for the time being. All we're interested in is the digital section on the left here. And of course we have 7 OR gates there. And now this is a particularly interesting thing, because this is another way we can trace what's high and what's low in our logic circuits. In this package you can set it by a button up here to show the traces. If I click that off, it doesn't show the traces anymore. If I click that on, it does show the traces, and it shows whatever is high in red and whatever is low in blue. And that's the most visible way to do it. That's the way I actually use. It's the easiest and most visible way to look at things. However, there is another one, which is this button here, and it's the logic probe. So if I click it on, I'm going to need to zoom in. If I put the logic probe here, you'll see the little H appears in it. If I put the logic probe here, you'll see the little L appears in it. High and low. So there we are. three ways to check what our logic is doing. So what we can do now is we can get on and we can actually draw a circuit. So although we're going to largely ignore the sounding system here, we're going to keep it in as it is the back end of the circuit we're going to create. And the circuit we're going to create is of course a digital one, and we're going to start with some OR gates. So devices, browse, digital basics, and a minor device class, gates, and then we pick a 2-in OR. And we place it. And what we can do next is we can duplicate it. And I want another 2 of those down here, so I'm going to go to Edit and duplicate those, like this. I want another 1 of them over here, and another 1 of them over here, and my final one over here. And now of course I need to wire them together, so what we'll do is this and this. Now there we are, all wired together, and now I need a logic switch to provide high or low inputs. So in digital animated, in digital I go to power and I choose a logic switch and place it in there. And again what I'm going to do is I'm going to hide the data. I don't really need it, and as that is selected I'm going to duplicate, and then I'm going to select both, and in the edit menu I'm going to duplicate, and I'm just going to go down like that, and the same again, oops, and the same again, and there we are. Now we've seen the tracer button there, and so what I'm going to do is I'm going to run the simulation, and it'll tell me that some parts of the simulation can't be simulated, and it'll be this transistor here. We'll ignore that. There we are. And what we'll do is we'll make sure that the system is working as we've drawn it. So here we go. And that appears to work. And so does that, and so does that, so does that, and that, and that, and that, and that. Good. So let's move it along a bit, because what I need to do now is I'm going to put some logic displays in. Oops, stop the run. So digital animated displays and logic displays. I want one here and another one about there, and then if I select both and duplicate again, about there. And what I'm going to do with these is they're going to be the boards. They're going to show me which zones are activated. Now in a real display board we'd probably use LEDs rather than a logic display, but it's the same thing. So oops, so let's carry on. Again, I'm going to select everything and hide all the text because I don't really need it. I'll refresh the screen. And let's make sure they work. And there we are. And so what that would tell me on a real display board is that zone 1 has been activated, or zone 2 has been activated, or zone 3, or 5 as we've got it here, or 4 or whatever we've got here, has been activated. Carrying on a little further then, and what we're going to do is we're going to wire into there. And this is of course a fire or a burglar alarm. Let's say it's a fire alarm, and what we'll see is that in zone 1 here, either an automatic sensor or somebody pushing a fire alarm puts a signal out like this. And if I put the run on, that would help. Puts a signal out like that. And what would happen is that it would go through, and we get a signal there to the base of the transistor, and the transistor would work the relay would energize, close, and this 24 volts would go through the siren and out to ground. Well, that's all well and good, but what we might need to do is we might need to run a test on the digital part without the sounder activating. We don't want every time we run a test on the digital part to have to evacuate the building. So, let's delete by using this button with the lightning flash on this wire. And what we're going to do is we're going to put in an AND gate. Oops. And there's the AND gate. And we're going to run a connection from the final output of our input system to the AND gate, and at the other input of the AND gate we're going to put in an inverter or a NOT gate, like that one. And then we're going to take another logic switch and put it there. From our AND gate we're going to run to our sounder, and we're going to take another logic display and yet another logic display, and we're going to wire that one into the logic switch directly, and that one into the output of the inverter. Now, what does this do for us? Well, let's run the system and see. If this switch is high, as it is, we can actually test without sending anything to the sounder. If, however, this switch is low, it's in live, it's armed. So we have it armed when the switch is low, and test when the switch is high. And of course that switch would be a secure switch. You'd either have it as a directly turned key switch or underneath a panel that you have to unlock to access. And the reason for having these two indicators is to tell us where we are. If that one's on, we're in test. If that one's on, we're in live. Now we have to go down and make sure everything works. So what we do is switch everything on. Let's go into test mode. And then we go around and switch everything off. And this should not go low until all inputs are low. So there we are. And the reason we do that is in case something's developed a fault. So for instance, let's delete that line. And now we go around and we'll switch everything on again. And switch everything off again. But we've still got two highs here. We've got two highs here, but this has gone low. And that isn't right. So we know automatically that in this zone something is wrong. And it's the fact that we've deleted the line. Put the line back in. And there we are. Good. So, that's really it for the digital section. And what we've done here is we've taken an OR gate and we've fanned it out so that we can have 8 inputs leading to 1 output. And we've done a test system and we've been able to simulate it successfully using our logic displays and the trace that's built into the package. We didn't use the logic probe this time, we didn't really need to, but it's there if we want it. And that would give us a working alarm system, developed entirely as a simulator. But there are also certain caveats, and we'll look at the certain caveats later. Well, to conclude this film then, what we'll do is we'll look at those caveats I mentioned, and it's to do with the inputs. And if you watch the videos I made before, you'll have heard me going on about things called pull-down resistors. And the inputs of the gates have to be tied reliably to ground if you want to use them in the way we did before. And the way we do that is we put in a resistor on each input. And there we go, the resistors. I just need to flip that round a little bit. Bear with me. There we are. Now, the value of a pull-down resistor is not that critical unless you're doing something extremely precise, and usually they shouldn't be less than 10k and they shouldn't be more than 100k, and 10k is my shortcut. And so what we're going to do is we're going to edit the device data to make that a 10k resistor. And there we are. And let's just zoom out a little bit here. There we are. And put in another one of these. Oops. And there we are. And the idea is to tie both to ground to avoid any floating voltages. Just like that. And the other thing is that we don't show normally in simulations the power inputs. Of course, for this you will have to have a positive DC input or a negative DC, so it'll have to go 5 volts, 0 volts. Really, with any kind of logic gate, you shouldn't be using more than 5 volts to work the inputs. And that's it. That really concludes our film. And this has been the last film for Unit 38, and I hope you've enjoyed the series. Thank you very much for watching.